Hello there. Now that we are done discussing the basics on continuity, I'll now share a theorem that showcases an important property of continuous functions. So, the Intermediate Value Theorem, or IVT for short, states that if f is continuous on the closed interval ab with the function value at the bounds to be different, then for every k between f of a and f of b, there exists c between a and b such that f of c is equal to k. So it's quite overwhelming. The definition is quite overwhelming, but what this tells us is that if we have a graph and x equals a and x equals b out here, since f is continuous on the closed interval ab, then we know that f of a and f of b are both defined. Moreover, since f is continuous, then there is a line that connects these two without gaps. Now, if we consider k in between f of a and f of b, then there exists a c between a and b such that the function value at c is k. So it's this one. Now, given this illustration, it's still quite hard to understand really. Like, what the heck? But to understand this better, let's have this illustration. So similar to a while ago, we'll have a and b out here, and then the function value f of a and f of b out here. And suppose we have this line out here, this line y equals k. And so we suppose otherwise. We suppose that this line out here, we suppose that the function f doesn't pass through this one. But we know that f is continuous. So how do we do this? So again, we know that f is continuous, and we suppose that the function f doesn't pass through this line. So let's try to figure this one out. Okay, I want to go here already, but again, we know that f is continuous, and we know that what we want is for our function to not pass through this line. So let's try to figure this out. Let's move over here, and we have no choice. We really need to pass to get over here. So as you can see, the intermediate value theorem just tells us that if we have a value, this one, if we have a value between f of a and f of b, let's move that again. There, if we have this value, we are sure that at whatever point, so if we choose this one, then we know that it would hit our function and there will be a c such that f of c is equal to k, like that. What we can do, what about, let's fix this one. Let's move this and this and this. Suppose I forgot this one. There. Wait a sec. Okay, let's move this first out here and there. Now, if we try to move this out here, but it's still in between f of a and f of b, then there would still be a c out here. There would still be a c such that f of c is equal to k. So basically, it's just technically common sense, but the intermediate value theorem helps define this idea formally. So I hope by this illustration, the idea on intermediate value theorem is now more understandable, since the definition is quite technical. So with that, let's try out some examples. Starting with this first one, we are given f of x to be 2x minus 5. Our goal here is to first verify that IVT holds for f in the closed interval 1 and 3. So before I start this one, you may pause the video, check the theorem previously, and try this one first on your own. Okay, good. So let's start. So to show that IVT holds, what we do is we show that the two assumptions in IVT hold. That is, f is continuous on the closed interval 1, 3, since that one, the closed interval 1, 3 is what is given in this one. And we show that f of 1 is not equal to f of 3. So the function value at the bounds are different. For the first one, clearly, since this one is a polynomial, then we know that f is continuous on the closed interval 1, 3. And more generally, f is continuous everywhere. So the first condition or assumption is true. Next, we check the function value at the bound, starting with f of 1. So just plug this one in out here. So we'll have 2 times 1 minus 5, or 2 minus 5, which simplifies to negative 3. For f of 3, this one is equal to 2 times 3 minus 5. Then this simplifies to 6 minus 5, or 1. And clearly, these two are not equal. So the second assumption is satisfied. So since the assumptions for IVT are both satisfied, we conclude that IVT holds for f in the closed interval 1, 3 in this case. So that is the answer for this first sub-item. We were successful in verifying that the IVT holds. Moving to the second sub-item. So is there a c in the open interval 1, 3 such that f of c is equal to negative 2? So again, you may pause the video to try this one first on your own. Okay, good. So let's start. So to solve this or to answer this problem, take note first that negative 2 is between negative 3 and 1, or more specifically, it is between f of 1 and f of 3. So we know this since we obtained the value of f of 1 out here and f of 3 out here. So we know that f of c is in between f of 1 and f of 3. Moreover, we have seen from A that IVT holds for f in this closed interval. Therefore, by IVT, by the definition, we know that for every k between f of 1 and f of 3, so in this case, instead of k, we have negative 2. So this is like the k that we mentioned in the definition. So by IVT, there exists c between 1 and 3 such that f of c is equal to negative 2. And so clearly, the answer for this one is yes. As easy as that. As an exercise, you can verify that the value of c out here is 3 over 2 or 1.5. So that's just easy. That isn't really that hard, but you may try that one. And before we move on to the second example, as a remark, take note that IVT is useful in locating roots of equations. And you'll see that later on in this next example. So we have x raised to 4 minus 7x squared plus x plus 4 equals 0. Our goal here is to show that the equation has a solution between negative 3 and negative 2. So before we solve this, you may try to solve this one first on your own. So as a hint, you will apply IVT on this interval. Okay, good. So let's start. So we first let f of x, we let this expression be f of x. So just take note of that one. And we take note, what does it mean to have a solution between -3 and -2? So we know that in equation, for us to have a solution occurs when we plug in a value. Say, so we know that if this one is f of x, a solution occur if, say, we plug in the value of c in this equation, and this one holds. So this means that this must be equal to 0 when we plug in c, like that. So it is a solution since we know that plugging in c would make the equality hold or true, something like that. So to define that, this one will have a solution between -3 and -2 if there exists a c in -3 between -3 and -2 such that f of c is equal to 0. So as you can see, this one is quite parallel already to the IVT definition. So far so good. And so let's try to apply IVT out here in the interval -3 and -2. First, again, we check the assumptions. So we check that, so again, this one is f. F is continuous on -3, -2, the closed interval, and f of -3 is not equal to f of negative. So we'll show this one. First, note that clearly f is continuous on the closed interval -3 and -2, since this one is a polynomial, and we know polynomial to be continuous everywhere. So we have f is continuous everywhere. Next, we check the function value at the bound, starting with f of -3. So plugging in -3 in our f will have -3 raised to 4 minus 7 times -3 squared plus -3 plus 4. This is equal to 81 minus 7 times 9 minus 3 plus 4. Or simplifying further, 81 minus 63 minus 3 plus 4. Or this is equal to 19. Next, we check f of -2. We do the same process, so plug in -2 in the function. This simplifies to 16 minus 7 times 4 minus 2 plus 4, or 16 minus 28 minus 2 plus 4, or simplifying, this is equal to -10. So clearly, these two are not equal. So since the two assumptions in IVT were satisfied, we then conclude that IVT holds for f in the closed interval -3, -2. So technically, the strategy that we used here is similar to the sub-item A in the first exam. Next, we'll try to do a similar process in the sub-item B for the first exam. So take note that 0 is between -10 and 19. Or 0 is between f of -2 and f of -3. So 0 out here acts like our f of c, seen here. Or like 0 is like our k in the definition. So given that, by IVT, since we know that it holds by IVT, we know that there exists c between -3 and -2 such that f of c is equal to 0. And what can you observe here? Observe that this out here is what we want, as we can see out here. Technically, this out here tells us that the equation has a solution between -3 and -2. And to illustrate this one, to understand much better, suppose if we have this graph out here, and we know that out here, at f of -2, we have -10, so that's like 1, 2, and suppose this one is -10, this one is -2, and we have f of -3, so it's around here, and 19, suppose that 19 is out here. We know that since f is continuous, so there's a certain line that connects these two. And since 1 is negative out here, so this one is f of negative 10. Oh, oops, that's wrong. This one is f of negative 2, and it is equal to negative 10. And this one out here is f of negative 3, and it is equal to 19. So we have just a different color. Ooh, there, again, to emphasize. There. So we have here from the positive side, and we have here from the negative side. And since f is continuous, we are sure that it would pass through the horizontal line. So we know that it will pass through x equals 0, or rather y equals 0 out here. So technically, if we check the bounds of a certain interval and one is positive and one is negative, the idea is by IVT, we are sure that there is a root in between these two intervals, since we will have f of c equals 0 in between them. So I hope you got that one correctly, and I hope that that explanation is understandable. I hope, but if not, you can comment it down below, and I'll try to do my best to reply and answer how this works properly. So that is the answer for this problem. And as an exercise, you may try to show that the equation also has a solution between negative 1 and 0. So we'll just do a process similar to this first sub-item. So yeah, that's it. I hope you enjoyed and learned a lot from this video. Feel free to comment down below your answers to the exercises mentioned in this video, as well as any recommendations and suggestions that you have for this video, this playlist, and this channel in general. So yeah, that's it, and that's all for this video.